My talk today is entitled Multimodal Data Fusion by Low-rank Tensor Approximations, and I will introduce you some of the results of my PhD works, which are related to a specific problem in remote sensing, which is the hyperspectral super-resolution. But before that, I will start with a very simple general introduction, and I will first remind some vocabulary regarding data fusion. So we usually call a measurement device a modality that is used to acquire data or signals that contain some information about a physical phenomenon we are interested in. Due to the large availability of modalities, there are often several datasets that contain partial information about the same phenomenon, and this is known as multimodality. To give you an example, in medical imaging, both functional magnetic resonance imaging and electroencephalogram are able to provide information about the brain activity. But today, my field of interest is remote sensing, in which both hyperspectral and multispectral images are able to characterize the composition of an airborne scene. To exploit the multimodality, the data fusion was defined in the literature as the analysis of several data sets in such a way that they can interact and inform each other. It has proved its interest in a variety of applications, but several issues need to be taken care of when designing a fusion model. First, because the available datasets have different sizes, resolutions, or noise contaminations that are not always compatible. Various fusion strategies and link between the modalities can be chosen, and the uncertainty phenomenon in the shared information must be carefully handled as well. In this talk today, I will focus on a specific fusion strategy that assigns symmetric roles for each observation, and I will address a specific remote sensing problem, which is hyperspectral super-resolution. So first, I'd like to remind the principle of spectral imaging quickly. So spectral images can be seen as data cubes with two spatial dimensions, represented by x and y, and one spectral dimension that is represented by lambda here. Roughly, what we can say is that each pixel of a spectral image contains the spectral signature of the material in that pixel. And this property is very interesting because it allows us to exploit these images in various applications, going from image classification to target detection, for instance. However, due to the physical limitations of the measurement devices, there exists a natural trade-off in the resolution of spectral images. On the first hand, we have hyperspectral images, or HSI, that have hundreds of spectral bands, meaning that they have a high spectral resolution. This comes at the cost of a small number of pixels, which means low spatial resolution. On the other hand, multispectral images, or MSI, have few spectral bands, which allows them to have high spatial resolution. To overcome the limitation of each measurement device, the hyperspectral super-resolution problem was proposed. It consists in recovering a super-resolution image, or SRI, from a hyperspectral and a multispectral image of the same scene. The super-resolution image that we wish to recover has both high spatial and high spectral resolutions. It's related to other problems in remote sensing, among which there is the pan-sharpening problem, which consists in merging a hyperspectral and a grayscale image, or the unmixing problem, which consists in extracting high-resolution spectral signatures and abundance maps from a super-resolution image. I can now introduce the observation model. And early observation models for the super-resolution problem were based on matrix models. A lot of them do exist, and they are based on matrix factorization. This model was widely used because it has good model fitting and possible interpretability. However, the model as it is presented now is non-unique. Fortunately, some additional diversities can be incorporated in order to build powerful uniqueness tools. But most importantly, this model fails at preserving the structure of higher dimensional observations, such as spectral images, for example. As a result, in this presentation, I will consider tensor models. So basically, a tensor is an array of p dimensions And today I will focus on data cubes, which means tensor of 3 dimensions. 3 diversities are available from the 3 dimensions, and this representation allows to preserve the multi-dimensional structure of the observations. Additionally, some low-rank tensor decompositions are unique, which is of interest for image reconstruction, for example. As a result, tensor modeling is suited for solving the super-resolution problem. Now, before going any further, I'd like to introduce 2 useful tensor operations that I will use during my talk. The first one is the mode product between a tensor and a matrix, and consists in multiplying the fibers that compose a tensor in one direction by a matrix. And this operation gives another tensor. Now, the second operation is called tensor unfoldings, and consists in transforming a tensor into a matrix by stacking the fibers of the tensor as the column of the resulting matrix. Note that these 2 operations can be performed along all the dimensions of the considered tensor. Several low-rank tensor decompositions do exist, and just note that they have different rank properties and uniqueness results. The most popular ones are the canonical polyadic decomposition, the Tucker decomposition that is obtained from the higher order singular value, and also the block term decomposition, which will be my decomposition of interest here. I am now ready to introduce the tensor observation model for hyperspectral super-resolution. So we have 2 observations, a hyperspectral image YH and a multispectral image YM of the same scene. The hyperspectral image has low spatial resolutions IH, JH, and high spectral resolution K, while the multispectral image has high spatial resolutions IJ and low spectral resolution KM. We assume that they are the graded version of a single super-resolution image that we call Y. And these images can be degraded by means of degradation matrices P1, P2, and P3 that are expressed in the set of equations here. For the hyperspectral image, P1 and P2 are Gaussian blurring and downsampling matrices, so we assume they are separable here. P3 is the spectral degradation matrix that contains the spectral response functions of the multispectral sensor. Most tensor approaches for the hyperspectral super-resolution problem reformulate the reconstruction as an optimization problem, which aims in fitting the observations with the degradation model, under the assumption that the resulting super-resolution image admits low rank. Note that the scalar lambda here controls the weights of the 2 low-resolution images in the cost function. However, the reconstruction problem is ill-posed because you wish to recover a large number of entries in the super-resolution image from a small number of observations. So we wish to make this problem well-posed, and for that we will use dimension reduction strategies such as low-rank decompositions. And in the table here, I ordered the different decompositions that we can consider by order of complexity, and I illustrate these results in the figure below. So what this figure tells us is that for wisely chosen ranks in tensor decompositions, we can highly decrease the complexity of the reconstruction problem, which means that we can have a low number of estimates, which will make the problem better posed, if I can tell it like this. So there are actually some variations to the tensor model that I introduced. On the first hand, we can consider blind models, which assume that some degradation operators are unknown. But the variation that I'm interested in today is called inter-image variability, and it regroups some variations in the acquisition conditions of the observations. They can be seasonal, atmospheric, or represent a term of spectral variability. So in this talk today, I will focus on the super-resolution problem, although my results can be a little more general than this specific problem, because I try to keep the model quite general. In the following part, I will introduce an approach to the super-resolution problem that is based on the block term decomposition. It accounts for spectral variability, and it is able to solve the fusion problem, but also the unmixing problem of the super-resolution image. And if time permits, I will say a few words on the statistical performance of this approach, using a Cramer-Rao bound that is able to account for random equality constraints. So now let me jump to the first part, which is my approach based on block term decomposition for joint fusion and unmixing of the unknown super-resolution image. Let me start with the problem at hand. As I quickly mentioned earlier, in practical scenarios, there are few satellites that embark both hyperspectral and multispectral sensors. As a result, most of the time, the two observations are acquired at different times, resulting in seasonal, atmospheric, or illumination variations, a phenomenon that is called inter-image variability. For example, in the figure below, we can see the variability around the crops and a little bit around the lake area. This variability requires the needs for flexible observation models that are able to take the variability into account. As a result, I will consider a slightly different model than the one I introduced a few slides before. We still have two observations, a hyperspectral image YH and a multispectral image YM of the same scene that are acquired at different times. But rather than considering that they are degraded versions of the same image, we consider two different super-resolution images, Y and Y tilde. And we will link these two images by means of an additive model, Y plus psi here, where psi is a tensor of variability. Again, this degradation model can be written by means of tensor equations, where we can see that the variability terms appear here. One problem with this model is that it is very ambiguous, because the tensor psi represents a general term of variability, which can be spectral, but also spatial. So in order to make this model well posed, we will need to make some assumption on the variability, and we will also use some low rank decompositions with very small rank to ensure that we can solve the problem. Today, I will use the block term decomposition with rank LL1, and this decomposition factorizes a tensor into terms A, B, and C, where A and B are matrices with rank L and C as vectors. And formally, we can express the BTD like this. What I find interesting with this decomposition is that it can provide a link with the linear mixing model that is a matrix model widely used in unmixing. Let me explain how. So first, we can consider that the AR-BR transpose terms can be seen as matrices SR, and due to the definition of the AB, they admit low rank L. So they can be seen as abundance maps. Similarly, the vectors CR here can be seen as spectral signatures for the earth material that is available in the tensor Y. Of course, in order to be interpretable, these factors must be entry-wise non-negative. But under this assumption, they can be seen as mixing models of the following form. So basically, under all these assumptions, it's possible to go from the LL1 model to the linear mixing model by simply unfolding the tensor in the spectral dimension. In this work, I made an assumption on the kind of variability that is available in our model. And this assumption says that the variability is only contained in the spectral domain. This is a rather strong assumption, but it always holds even with a small acquisition time difference between the observations. So how does it translate? So basically, the factor C in the spectral dimension of the LL1 model can be linked to the other factor, C tilde, of the underlying the two super-resolution image by an additive model. And psi here is a matrix that represents spectral variability. It is this spectral variability only represents a less general kind of variability than in a tensor psi, but it also allows for less restrictive recovery conditions for the super resolution image that we wish to obtain. So under these assumptions, we can express the block term decompositions of the two super resolution images, y and y tilde, and that of the variability tensor psi. So note that they have the same spatial factors, AR, BR transpose, but different spectral factors, respectively C, C tilde, and psi, that can be linked through the model above. Now I will introduce the proposed approach. For a little bit of context, although there are lots of tensor-based super resolution methods nowadays, the joint problem of fusion and unmixing was not addressed with tensor modeling. On the other hand, there are some matrix approaches that are able to perform both fusion and unmixing, but their conditions for exact recovery were based on additional constraints on the low-rank factors. So my approach is a bit of a mix of these three. So it's a tensor-based approach for both fusion and unmixing. Let me explain this procedure. So our goal here is to recover the super resolution tensor as well as the variability tensor to have some information about what's happening. So this is the fusion part, and the unmixing part is also to recover the non-negative LN1 factors that can be interpreted as mixing factors. So we have our degradation model that I introduced before, and starting from our observations, what can we obtain? So from the hyperspectral image, we can obtain high-resolution spectral signatures. And from the multispectral image, we can obtain high-resolution abundance maps. And given the LL1 BTD model, we can recover the super-resolution image Y. Similarly, the multispectral image YM also gives us low-resolution spectral signatures that are corrupted by the variability phenomenon. For this approach, I have some conditions for exact recovery, and the following theorem holds. So if we consider that we are in the noiseless case and that our degradation model is valid, then we can recover the super-resolution image Y, and also a degraded version of the super-resolution image Y tilde in the spectral dimension, under some conditions on the rungs of the decomposition that are linked to the dimensions of the observations, basically. What you should remember from this theorem is that we can only recover a portion of the super-resolution image Y tilde. So we can only obtain a degraded variability in the spectral dimension. However, what's interesting is that this theorem also holds for recovery of the low-rank factors. So it's suited for both the fusion and the unmixing part of the problem. So the first step towards this procedure is to consider an approach for fusion only. It is based on solving the optimization problem, which consists in minimizing J. Again, this cost function is composed of two fitting terms between the observations and their block term decompositions that you can see here, and where the P1, P2 appear and the variability is translated here. I introduced the first algorithm that is called BTD-Var, and that consists in updating the low-rank factors in an alternating fashion. There is also a normalization step of the factors in the spectral dimension to avoid convergence issues. And finally, using the block term decomposition model and the variability assumptions that we made before, we can reconstruct the super-resolution image and a degraded version of the variability tensor. However, because no non-negativity constraints were enforced, this approach was suited for fusion only, but not unmixing. As a result, I designed a second algorithm that is constrained. And this algorithm aims at minimizing the cost function J, subject to some non-negativity constraints on the factors, so the spectral signatures, C and C tilde, but also the low-rank abundance maps characterized by the AR-BR transpose. And this resulted in a second algorithm called CNN BTD-Var, so constrained non-negative, which is similar to the previous one. And the non-negativity constraints are handled using alternating direction method of multipliers. Additionally, some low-rank constraints on the abundance maps can be enforced because they're important factors now. And this algorithm is suited for both the fusion and the unmixing parts of the problem. Now, let me illustrate the results of the performance of this approach with some simulations. And let me first explain the fusion setup. So we have available a super resolution image Y and a multispectral image YM that are acquired by different sensors at different times. From the super resolution image, we will generate the spatial degradation matrices P1 and P2 to generate the hyperspectral image. Then white Gaussian noise will be added to the observations in order to have around 30 dB SNR. Then the spectral bands of the observations will be normalized to avoid convergence issues. And in the following slides, I will compare my algorithms to state-of-the-art approaches. Some of them are matrix-based and some of them are tensor-based. And in particular, the tensor-based methods do not account for variability at all. I will also consider two outliers, if I can say it like this. The first one is foo-var. It's matrix-based and accounts for spectral variability. And CB*, which is an algorithm that is based on tensor decompositions and accounts for localized changes, so a general form of variability. And I will use a real data set, which is called Lockwood and has some small acquisition time difference between the observations. So in the table, I show different reconstruction metrics. So the most important one is the reconstruction SNR, but there is also cross-correlation, spectral angle mapper, that all give an idea of closeness to the real image. And I also give the computation time of each method. So first, what we can see is that the two algorithms that I proposed, BTD-Var and CNN BTD-Var, give some of the best reconstruction metrics. They are followed by some matrix approaches and also by CB*, which is a tensor approach that accounts for variability. Note that the two tensor approaches that I consider do not account for variability at all, hence they give the worst reconstruction metrics in this table. Also interesting to see is the computational complexity for this implementation. And basically, the computation time of my algorithms are comparable to those of some other matrix approaches. Please note that this dataset is an example where this approach works well because there is small variability. Usually what happens is that CB* performs really, really well because it accounts for a general form of variability, so it's suited even for long acquisition time difference. However, one specific drawback of this approach is its computation time, of course. In the figures below, I show some reconstructed spectral bands of the super resolution image and the tensor variability, just to give some idea that the proposed approach performs well visually. Let me now jump to the unmixing part of the problem, and I will have a different setup. So I'll consider unmixing of the unknown super resolution image Y, and I will compare my algorithm CNN BTD-Var to a matrix approach that's called CNMF, and also two-step procedures that are based on tensor methods. So the first step is to perform a reconstruction of the SRI by CB*, because it usually gives the best reconstruction metrics. And reconstruction is then followed by a traditional unmixing algorithm that is performed on the reconstructed image itself. Here I will consider another real data set, which has some longer acquisition time difference and represents a scene above Lake Tahoe. It's suited for mixing because it has three main end members, the water represented by the lake, the soil, and also the vegetation. So in the figures, I will show the reference spectra and abundance maps, and also the reconstructed one by each of the approach. So CNN BTD-Var and the two-step procedures and CNMF. So first, what we can see is that the proposed approach allows to recover all the spectral signature accurately, while, for instance, CNMF did not perform well for water. Now, regarding the abundance maps, we can also recover them correctly, although with a smaller spatial resolution than other state-of-the-art methods. And this is because we enforced low-rank constraints on these matrices. However, what's interesting to note is that we can there is a good separability between the abundance maps without the need for additional constraints, such as a minimum volume, for example, that are enforced in BMDR ADMM, for example. If we have a closer look at the variability model, we can also recover the variability factor. That gives us some idea of which spectral bands in the images are more corrupted by the variability. So this figure shows us that we can recover correctly the degraded spectral signatures that contain some variability, but also the degraded variability factor itself. And in the second row of this plot, we can see that for the water material, the band corresponding to the blue wavelengths is the most impacted by variability, while for the soil and vegetation materials, the bands that are the most impacted are the orange to infrared wavelengths. So in a nutshell, I use a flexible tensor model that accounts for inter-image variability to propose a joint solution for fusion and unmixing of the super-resolution image. I introduced two algorithms with recovery guarantees that allow that we can solve both parts of the problem. And although these conditions are noiseless, they actually provide a link with the statistical identifiability of the model. So now, considering that these algorithms perform well, a question that we can ask ourselves is, are they efficient? Well, the answer is positive, because we can conduct performance analysis for the algorithm BTD-Var, but it required to design a new constraint Kramer-Rao bound that is able to account for random uncertainties. And this will, and quickly now I will introduce the work related to this performance analysis. So the following part will be part of my thesis work still. That was a general analysis of performance bounds for coupled tensor models under constraints. So let me first give you a very general framework of what I did. So I derived Kramer-Rao bounds for coupled tensor models. So first, of course, I had to choose the model parameters. They can be the low-rank factors, but in the case of image reconstruction, the parameter of interest is rather the reconstructed tensor itself. Then, because we are dealing with coupled models, I had to identify the constraints on the model parameters and apply a formula according to the scenario, whether we consider that there are no constraints, some constraints, or all the constraints of the model. And this led us to the calculation of the constraint Kramer-Rao bound. And finally, I used this bound to evaluate the statistical performance of some estimators. So my contribution regarding this part first addressed the canonical poietic model, but today I'm interested in assessing the performance of the approach that I just introduced. So I will use the randomly constrained Kramer-Rao bound that I will apply to coupled model with block term decomposition and a random variability phenomena. So let me first give you an idea. Maybe some of you are familiar with this notation. When we are dealing with a coupled model, under this, we use the constrained Kramer-Rao bound. In this work, I assume that my model was statistically identifiable. However, a problem with this standard tool is that when the constraints on the model parameters depend on an additional random vector, this bound is non-informative. However, it still remains a tool of great interest for design of a system of measurements and performance analysis in the presence of of deterministic constraints, of course, which leads us to the introduction of a random parameter that we'll refer to under the term theta r. Let me quickly explain now how I computed the randomly constrained Cramer-Rao bound. So the first step to obtain this bound was to consider a locally unbiased estimator conditionally to the value of this random parameter that's bothering us here. So after some derivation, we can obtain the expression of the conditional constraint Cramer-Rao bound that is conditional, of course, to the value of this random parameter. And the randomly constrained bound, so the RCCRB, is obtained as the expectation of this bound over the model parameter of interest and the random parameter theta r. And it's a lower bound on the on constraint estimation when the constraints involved a random parameter. Now, since we are considering LL1 estimation, I will remind some the optimization problems that we are dealing with. So the first one is state of the art and is an optimization problem that does not account for variability at all. So basically, you have two observations, y1, y2, and that admit degraded block term decompositions. And we want to reconstruct an image by fitting this cost function. This is a fully coupled model because you can see that there are some constraints, P1, P2, P3, along the three dimensions, but it does not account for variability. Whereas the algorithm BTD-Var that I designed accounts for this variability phenomenon. And a way to consider variability is to consider a blind model, meaning that I still know the relationships between the A2, P1, A2 in the spatial dimensions, but the variability is hidden in the C2 and C1 factor here, which I can't link together. So for some results, here is what I computed. I was interested in performance for image reconstruction, and I considered state-of-the-art algorithm, LL1 ALS, that does not account for variability, and also the proposed approach, which is BTD-Var. And I compared them with the standard tool, the constraint Cramer-Rao bound, and the new RCCRB that accounts for the variability phenomenon. And to have a clear idea of what's happening in the asymptotic regime here, we can have a look at the lowest right plot. So the best performance of the model is obtained by the red dotted line here and correspond to the RCCRB. Attached with the green diamonds, you can see the performance of a clairvoyant estimator that would be able to estimate the variability phenomenon. On the other hand, the worst performance were given by the standard deterministic tools, so the CCRB, and the LL1 ALS algorithm, the red circles, that did not account for the variability. So where is BTD-Var? Well, BTD-Var is in the middle of these two curves here. We assess this performance using the partially coupled randomly constrained Cramer-Rao bound, and the performance of BTD-Var are shown in the blue crosses. So what we can see is that there is a gain in considering a blind model compared to assuming that there is no variability at all. And of course, BTD-Var does not reach the best performance of the model because it's unable to estimate the variability phenomenon. But it also gives room to design a new estimator that would be able to estimate this bound, provided that it could give an estimate of the variability phenomenon. So to wrap up, I proposed an algorithm that is better than the state-of-the-art without variability, but still does not reach the best performance of the model, which gives room for future works. The work that I presented today is attached to some softwares that are available on my personal webpage. But for now, I think this is time for questions. So I would like to thank you for your attention.